In this video, I'd like to explain vector algebra. What is exactly a vector algebra? We know that a vector has a magnitude and a direction. So for example, if I draw a vector, it has a direction pointing in that way, and it also has a magnitude, which is the length of the vector. And I'd like to construct an algebra. So we might ask questions, what exactly happens if I scale this vector by like doubling it? Well, we know that the new vector could be drawn by just twice as big, so the magnitude is stretched, but the direction still points in that direction. So if I add two vectors, we can also do a tip-to-tail construction of adding vectors. Hopefully you've understood this at this point. But how do we algebraically manipulate vectors so that we can do calculations? And before I explain that idea of exactly how to algebraically manipulate vectors, let's ask a problem that seems very subtle, but imagine that I'm on the surface of the Earth, maybe at the equator, or at some point. Maybe I'm in New York City, and here I am at New York City, NYC, or actually let's just make it that I'm some point on the surface of the Earth. X marks the spot, so here I am, X. And basically I'm going to assume that this way, that direction is called east, and the other side is west, and up is north, and down is south. So here we go, like symbol letters that define the directions, the four directions of north, south, west, and east. And I'm going to ask myself the following problem. Imagine I'm at the origin of some system. I'm at some point in space, or in some point on the surface of the Earth, and I do the following. I travel 5 meters east, and then I travel 7 meters north, and then I travel 3 meters west, and then I travel 4 meters south, and then let's add one more statement. Let's say I traveled 2 meters west. And the question is, where am I? Oops. So I've written down the instructions. So I can say I've traveled 5 meters east, 7 meters north, 3 meters west, 4 meters south, 2 meters west. But is there some kind of an algebraic system I could represent this by? And let's verify. So I could actually go to a graph and start counting up all the regions. So I'd say 1, 2, 3, 4, 5. So I've traveled 5 meters east. So that's this. I've traveled 5 meters east. Then I've traveled 7 meters north. So let's go 1, 2, 3, 4, 5, 6, and I'm a little too high, so I'll just move up the graph a little bit. And so I've actually moved myself at the origin. So I've now traveled up a height of 7 meters. So it's 1, 2, 3, 4, 5, 6, and 7. So I'm over here. I'm going straight up. I've reached this point. So there I am. I am at the position of 5 meters this way, 7 meters up. I'll even write it down. Here's 7 meters and 5 meters. And then I've traveled 3 meters west. Okay, so west, that means that I've traveled 1, 2, 3. So I should be 5 meters. So going across, I'm 3 meters this way. So that means that I've traveled 2 meters. Where is this position? I'm 2 meters in the east direction and 7 meters up. So that's my current location. And then I travel 4 meters south. So let's go down. 1, 2, 3, and 4. So right now this is 4 meters. So at this point, right, we should be, well, this is 4 meters. There's 3 meters left. So we should be at a position of 3. So this position, I should write it down over here, but I'm at this point. And then I ask myself, I did 2 meters west. What is 2 meters west? I traveled this way to this point. And we could actually construct it, and I'm sure we could reasonably get an answer, but the problem is I I would like to construct this algebraically. How could I do it? Well, let's imagine I say that when I add 5 meters east, let's do some abstraction. So instead of calling it east, I'll call it something called I vector. So whenever you see the I vector, right, it means east. And west. Well, west, right? I'm not sure how to say west, right? But maybe I should think of east. And so east, right, is the direction that way, east. It's in that direction. But what is west? Well, west is the opposite of east, so maybe I could represent it by minus I. And how about north? Well, north, I'm going to represent that direction called north by an abstract symbol. So I don't want to keep writing east and west and north and south. I want to represent them by symbols. So how about if I use a symbol like J? So J is going to be the direction north. Whenever you see the symbol J, I'm going to represent it by, or every time I see the symbol J, it's going to represent the direction north, straight up. Well, south is the opposite of north, so I'm going to represent that by minus J. So we seem to have constructed a simplification of this and said that what's 3 meters east, 7 meters north, 3 meters west, 4 meters south, and 2 meters west. Well, I've reduced this, right, into a symbolic representation. I'm not going to represent meters. What I'll do instead say is that this corresponds to 5, and I'm going east. Instead of east, I'm going to use a symbol with an I hat. So that means that I've traveled 5 meters east. It's an abbreviation for this. Here is 7 meters north. What's 7 meters north? Well, north is an abbreviation for the symbol J hat. And later we'll call these unit vectors, but that's not important. Not that it's a unit vector, but that this symbol J hat and I hat represent a direction. So in this case, I hat represents the east direction. J hat represents the north direction. So in this case, this is 7J. How about 3 meters west? Well, 3 meters west is really, I could write it one way. I could say this is 3 meters minus I, which is an abbreviation for west, which is minus I. But I can also write this in saying, if I travel 3 meters east, it is the same thing as if I travel 3 meters west, it is the same thing as traveling negative 3 meters east. So the minus I, I'm going to pull that out and say this is really minus 3I. So how do I read this? I have traveled negative 3 meters east, which is really 3 meters west. So let me make sure you understand this. So this is, when I say negative 3I, it really means I've traveled negative 3 meters, going backwards, in the east direction. That's what west is. So east is really the negative of west. And that's why I actually selected minus I. So this represents me traveling 3 meters west. How about 4 meters south? So 4 meters south is, I would say it's 4 meters times representing that symbol. So this number represents the amount of travel in that direction. So I've traveled in the minus J direction. The opposite of north is south. So I'm going to say it's minus J. So whenever I see the symbol J, it represents the north symbol. But if I travel 4 meters south, that's the same thing as saying it is negative 4 meters in the north direction. So remember, this is the negative 4 north is really exactly the same as 4 meters south. This is the negative of north. So what I'm doing is I'm constructing an algebra. And this algebra right now is like associating some abstract symbol, I and J, which are variables, which are not, varying, but it is there's some constants. There's something abstract, much like if I say some 7 meters. What is 7 meters? What is a meter? A meter is an abstract variable that represents a quantity. In this case, it happens to represent a unit of distance. So is this. This I hat and J hat represents a quantity. I hat represents a quantity which represents the direction of east. The J hat, right, represents the direction of north. So whenever you see those symbols, right, all it represents means that you are traveling minus 3 meters in the east direction, and which means you're actually traveling in the west direction by 3 meters. And minus 4J is you're traveling negative 4 meters in the north direction. So how about 2 meters west? 2 meters west is actually 2, but west is really minus I, negative of the east, the opposite of east. And then I could represent that by, let me erase this side and this side so I can get some space in here. So I can say that traveling 2 meters west is really traveling negative 2 meters east, negative 2 meters east. And how about if I represent that the motion of adding, of doing this followed by this, plus this, right, is really a plus symbol. Do these plus symbol means anything? Actually, to us, it really means literally and. It doesn't have any meaning. So if I take this as a whole, right, I could represent 5 meters east. So I represented that by 5I. I've traveled 5 meters east. And the plus symbol doesn't mean anything. It's just an abstract notation for us to represent the symbol saying followed by and. How about 5I plus 7? I went 7 meters north. That's 7J. And then I moved 3 meters in the negative 3 meters in the east direction. So it's minus 3I. And then I went 4 meters south, which is really negative 4 meters north. So that's represented by plus negative 4J. And then finally, I went 2 meters west, which is adding plus negative 2 meters to the west, to the east, I'm sorry. So we have constructed this motion, right, of encapsulated in a bunch of symbols. These symbols, right, I'm going to start now manipulating. And just to get you an idea, whatever this position is, I've traveled 5 meters east, 7 meters J, and minus 3 meters. And the first you ask yourself, just double check, verify you understand what this plus means. This plus has no meaning. It's just a placeholder for saying and. I traveled 5 meters east and 7 meters north and 3 meters west and 4 meters south and 2 meters west. It doesn't have any meaning. The plus sign in vectors, right, doesn't have any meaning. So let's take a look at what exactly happens. I do know one thing. Now the question is, so before I explain this a little bit further, right, let me erase this on the side and let's make sure you understand what we're saying so far. So this equation that I've written, it's an abstract algebra, and I'll show it's an abstract algebra, but I haven't shown you what an algebra is. Mathematics and algebra is basically any set of symbols that you manipulate with addition and multiplication. And I'll discuss this in a little more detail. It has more details in discussing like groups and rings and stuff, but let's not discuss those ideas. But let's be very concrete as a science major, right, what these things mean. These plus means absolutely nothing. This plus and this plus and this plus. It's just a placeholder for the word and. So this is reading off this. I traveled 5 meters east and 7 meters north and negative 3 meters east and negative 4 meters north and negative 2 meters east. That's what this represents. Now, I want to ask another question before I explain how to manipulate this a little bit further. And the question is, oh, I'm out of markers. Let me get another marker. Somebody asks you, right, what is 2I plus 3J mean? We know what it means. We now know what it means. If I, right, is the direction east, and J hat, right, is the direction north, this is actually a statement saying 2 meters east, and this is the plus sign, and then 3 meters north. But the question is that the same, right, as writing another symbol? What if I write down 3J plus 2I? Are these two things the same? Well, let's see. This is the statement that says travel 3 meters north and 2 meters east. And actually, let me put on the next line so we can represent. Are these two quantities the same? 2i plus 3j. And so imagine I drew a graph, and I can mark off the direction. So here is I hat, and here's a j hat. So they represent directions. I hat is going to be the direction east, and j hat is going to be the direction north. So I've traveled so let's read it off. I have traveled 2 meters east, 2i, 1, 2, I'm over here, and I'm over here from the origin. I've moved over 2 meters. Each step is 1 meter. And then I've traveled 3 meters up, north. So I've traveled here. I'm over here. Is that the same point as this? Is 3j plus 2y? Well, I've traveled 1, 2, 3. Whoops. My units lengths are not exactly the same, so let me do that again. I've traveled a 1 unit, and then a 2 unit, and then 3 units. So I've traveled 3 meters north. I'm over here now. And now I travel 2 meters east. 1, 2 along here. And guess what? I'm at the same point. That means that if I think graphically, right, traveling 3 meters, 2 meters east, and 3 meters up, right, is exactly the same as 3 meters up and 2 meters to the right. That means that 3j plus 2i is exactly the same point in space, right, as 2i plus 3j. So what you're saying literally is that traveling 3 meters north and then 2 meters east is exactly the same as traveling 2 meters east and then 3 meters north. They are the same point. What we're doing is we're constructing an algebra. Basically, we're constructing an algebra that says that, and if you're in mathematics, right, you'd actually say that there's a commutation relation between, with the addition operator. You're saying that something plus something, A, quantity A, plus some quantity B is exactly the same as a quantity B plus quantity A. That, if you're in mathematics, right, we might construct something, and we call this a commutation relation. It's commutative. We'd say that the property of adding two vectors together is commutative. But where is it coming from? That idea is that, well, it doesn't matter what path I take, whether I go this first and then followed by this is exactly the same as this and this. So this is an example of adding vectors. Now the next question is, well, does it matter that, so this A plus B is equal, that's nice, but how about scaling? Does scaling also do the same thing? So what you're saying is that you can actually show that. So let me ask you a different way. Let's go back to the plus sign, make sure you fully understand this. So if I instead put 2i plus 3i, is it exactly the same as 3i plus 2i? So this is saying travel 2 meters east followed by and 3 meters east. So you'd be at the point 5 meters east. And here, right, so if I could draw it graphically, I'd say I traveled here 2 meters east, and now I travel 1, 2, 3, I'm over here. Where am I? I'm 5 meters east. So before, right, this didn't have a meaning, but we could actually replace this with 5i. But is it the same as 3 meters east, traveling 3 meters east and followed by 2 meters east? So we travel 3 meters east and we're up to here, and I travel 2 meters further. I'm at the same point 5i. So it's kind of really interesting that when you have like symbols, right, or different symbols, like if I could replace with j's and j's, they still commute. So the addition of two vectors called 2i plus 3j, remember what it means, 2 meters east and adding another vector 3 meters east gives me the same thing as 3 meters east and 2 meters east. But we can also contract it and say 2 meters plus 3 meters I. Just looking at the i's, I can say it's really 2 plus 3 times I. I've traveled 5 meters east. I'm doing these steps to show you that this is how the algebra that you see in mathematics, in vector spaces, there are several rules, like maybe 8 or 9 rules or so for vector spaces. So there's things like addition, commutation, addition, distribution of scalar multiplication over addition. And they're all abstract. But where did they come from? They're coming from these ideas. And that's kind of important as a scientist, right? As a scientist, we're constructing new algebras. Some of them we can define as some kind of an abstract algebraic system. But these things are coming directly from our ideas of moving to the left, moving to the right. But anyway, let me continue this. So what if I ask myself, right, I travel 2 meters east and then 3 meters north. Hopefully you're reading this now directly. And what if, so I'll draw it graphically. So here is my origin. I've traveled 1, 2, I'm at this point 2 meters east. So this is east and this is north. And then I traveled 1, 2, 3. So I've gone up from here all the way up to here. I'm over here. And so we could say this represents an arrow drawn from the origin to this point. The question is, what happens if I basically double this? This vector I double. So I'm doing something called scalar multiplication. Scalar multiplication. Where would I be? Well, I know graphically what it means. I take this length and I double it. So I'm over here now. So I take this length and I draw it over here and put a little arrow there and draw it. So I've doubled the length. So graphically I'd say this is twice as big, right? But if you think about it carefully, where would I be? Well, I was 3 meters north, and if I double that, if you take a triangle and double the length of a triangle, the hypotenuse, right, you're actually doubling both the legs at the same time. So what is the length of this here? Well, before, right, this was 2 on this side and 3, but if I look at this length, it's 4, and this length is 6. The legs have been extended. So when I double a vector, you're actually doubling both the legs. So the direction of this arrow has been doubled from here to here to here to here. And where would I be? Well, I would be at the location of 4 meters east and 6 meters north. But guess what? This looks exactly like as if this point here is exactly the same thing as 4i plus 6j. And if you think about it a little carefully, right, what you're really saying, right, is that 2 scales each of the directions, right, by the same amount. Or I could say it's really 2 times 2i plus 2 times 3i, j, and which is exactly 4i plus 6j. So we can construct this algebra, this abstract algebra, right, and eventually make axioms out of this, right? And these axioms, right, are mathematically, right? You'll actually, if you're taking mathematics and you're taking linear algebra and you're actually doing analysis, and they'll start defining an abstract vector space over some field. The scalar multiplication is sometimes called a field, and so if you're working in real numbers, we don't have to worry about that. Most of the fields that introductory physics classes talk about are basically real numbers. But there are fields, other fields too, like for example complex numbers, quaternions, octonions. These are other fields. And these fields, right, we can define objects called vectors. In this case, right, we're taking a two-dimensional vector representing east and north and constructing an algebra. But this algebra, right, don't think this is an abstract algebra. It's coming from somewhere. We're constructing it from our understanding of east and north. And so the question is, look at this. If I travel 5 east and 7, so this is like 5 east and then 7 north and -3 east and -4 north and -2 east, does it matter, right? Traveling north, does it change? So if somebody asked you, right? So imagine I'm somewhere in a position. So here I am. So I'll do another example, and I'm trying to construct the algebra. And we can actually go through these steps in a little more detail, but if I look at this, right, I now travel to a point 5i. What does that mean? I've traveled 2 meters east, and I've traveled 3 meters north, and now I've traveled 5 meters east. Where am I? And if you kind of think about it very carefully, you'll see that 3j, right, 3 meters north, right, doesn't really affect how much you've moved east. And if you think about it, look carefully, you'll actually see that this 5i and 2i, right, still gives you 7 meters. So if you travel 2 meters east and then 5 meters east, you're going to be at position 7 meters east. And your north position doesn't change. The amount of northness, or negative northness, doesn't change. So what you've done is really move this operation into the other side and said 2i plus 5j. So these two things can compute even if they are different. So what you're saying is literally that this is exactly the same thing as 2i plus 3j, and we're constructing. Actually, I think I made it a little complicated, so I'll just write it in one shot. So this and this mean exactly the same. I have traveled 2 meters east and 5 meters east and 3 meters north. The order of this representation doesn't matter. But if it's in the east direction, right, I can put these together and say I'm now at 7i and then 3j. Where am I located? If I've traveled 2 meters east and then 3 meters north and then I've traveled 5 meters east, I will be at 7 meters east and 3 meters north. So the order of these symbols, right, when you add them, it doesn't matter. So take a look at this equation again. What I'm trying to say is that this summation, and this is a question that most people will probably get it wrong. If I ask you the following, if I take a random order of these sequence of steps, right, would I be at the same position? If I take a different sequence of steps, right, so I do this first, and then this, and then this, and then this and this, would I be at the same location? Well, if you do this in algebraic systems, right, we can rearrange them in any order and you'll see you'll always get the same point. Where would I be? Well, this is kind of really difficult because it looks like all these symbols, but I can put all the i's next to each other. So I'll do this with the next statement that says 5i. So here's my i's. There's a minus 3i, so I'll put a minus 3i. And then there's a plus negative 2i. Okay, so I rearrange them because the order doesn't matter. Now 7j and plus negative 4j, so I'll put that in the next line. So actually, I think I have enough space. Hopefully you can see everything. So I'll put 7j, and then plus negative 4j. And this 5, right, this I is going to be 5 plus negative 3. I can do that because if I'm traveling in east by this amount, that's the same thing as traveling. So if I say I traveled 5 meters east and I've traveled negative 3 meters east and negative 2 meters east, I can collapse that into a simple value of saying it's 5 plus negative 3 plus negative 2i. And 7j plus negative 4 is really 7 plus negative 4 north. And so we get this point, right, which is 5 plus negative 3, negative 5, which would be 0i. So my eastness is exactly the same as my original point. And 7 plus negative 4 is 3j. That's where I am. I am 3 meters north of my original location after all these steps. And does it matter what the order of the sequence of steps? Well, no. If I do it algebraically, I can manipulate this any way you want. Basically, you'll actually see that I'm still at 3 meters north. It hasn't changed. So what I'm showing you, right, is the construction of an algebraic system, right, where we can actually construct a vector, right, and this construction is right, leads us to an algebraic system. So this construction of taking English words and converting them to algebraic system, right, and then noticing things are the same and modifying these variables, right, we get something. And these rules, right, we call these rules a vector space. These elements, right, that form these rules, with these rules, right, we call it as a vector space. And this whole idea, right, sometimes people call this something simply as vector algebra. So I wanted you to get an idea exactly what this means to make sure you fully appreciate that this is not something abstract coming from nowhere. It's coming from something that you see every day. And you can see it in terms of symmetries, for example, in group theory. But these are not abstract ideas. They're coming from scientists who understand that, oh yeah, I'm just taking something that I write every day in English, and then we're simplifying in terms of an algebra. So the whole point of this algebra is that I don't waste time writing like this. In English, it's very difficult to manipulate symbols. But if I write it algebraically, I can move things around and add and subtract and scale and things very well. But anyway, in this video, I just wanted to introduce you to the idea of a vector algebra, or vector algebra. And this vector algebra, right, is basically the idea of scaling and adding vectors together. Okay, so in the next video, I'll start explaining exactly how to manipulate, and actually I'll give you examples. So hopefully you understood exactly where this is coming from. So don't think that it's coming from left field. It's not. These are ideas that are just coming from everyday intuition and your understanding of the English language, and saying that these symbols, right, are just symbols, like I and J are just directions for saying east, north, and minus I is west, and minus J is south, and so on.